Okay, so today it will be our last lecture. On Wednesday, we will do our final presentations. So for today's lecture, I would like to talk about some new topics which I didn't have time to cover in previous years. So first of all, I want to talk about hypothesis testing, right? And the distribution of the test statistic under the null. And also we want to do asymptotics as well. So just as a recall of what we did in lecture 12, so where we talk about the MLE, and that was a Zoom lecture. So I want to just review some of the key facts we use in that lecture. So we are going to continue using them today. So our random sample of size n, our IID from a distribution. Here we're going to use the probability density function PDF to be noted. So we call this key parameter theta. Okay, and we are assuming that theta equals theta 0 is the true parameter value. We want to estimate this. So when we do MLE, what we are actually writing down is the log likelihood. Okay, I'll just directly write it. The log likelihood will take the form lowercase l at a value theta is defined as a sum, which was a product before taking the log because of the independence. But after the log, it becomes a sum. I denote it by Li theta, where the ith term is basically the log density of the ith data point at this value theta. Okay, so this is how we write down the log likelihood. Based on this, we would have the MLE, maximum likelihood estimator, denoted by theta hat n, will be the maximizer of this log likelihood. This is how we did what we did. Okay, so there are three key results from this log likelihood MLE derivation. So first of all, we would need some regularity condition. Okay, so the regularity conditions are on the density. Okay, what we need is we can change the first order differentiation and integration with respect to theta. So what I mean is that we can move this differentiation inside because we know this is equal to 0 since it's a density, right? So what we need is that when we take the differentiation, it's integration is 0. So we are changing the order. And also for the second order derivative. So this implies that it's at least twice differentiable, the density. Okay, so under these two things, what we actually have is that to find the maximizer of this log likelihood, assuming that it has a global maximum, okay, and it's twice differentiable, then what we can actually know is that we take the derivative of a log likelihood and evaluate at the MLE, it's 0. So which means the MLE is a solution of the log of this equation, okay, of the L prime theta equal to 0, and theta hat 0 is just the solution to it. It is where the first derivative of log likelihood is equal to 0. Okay, so with this and with this log likelihood form, one thing we can see is the first important result, I'll call result 1, is about this. If I look at the first derivative of L, log likelihood at the true value theta 0, what do I have? Based on the sum, you can see it is essentially equal to d theta. That's where this derivative is against. Right? This is it. And we know that it's the very important fact is this is a sum of IID, right? It's the sum of n IIDs. So central limit theorem can be applied here. So based on the fact that we know the expectation of each of these terms has 0 expectation. This is because of the fact I just write here, okay? It's actually based on this. Okay, so then by CLT, we will have a very important result. Divide this by n and it becomes an average and its mean is 0. Okay, so we would have basically root m times the average of this, okay? That is 1 over m, okay? Will converge in law. Maybe I'll write to the second line. Normal distribution, and what's its variance? Variance of this, we also know this. This is actually Fisher information. Okay, variance of each term. And we call that Fisher information at theta 0. This is the first result we have for the what? This thing, okay? And if I simplify this a little bit, I would just have 1 over root m, L prime theta 0 converges in law to this normal 0 mean Fisher information variance. That's the first result. Okay, for the second result, let's see. What if I take another differentiation? So if I do, okay, again, I can have it as a sum of IID. Okay, and I know what? I actually know what's the expectation of each. That's if I take the negative of d theta square. This is something we derived also. This is also equal to Fisher information. Okay, so now you see each term's negativity has expectation equal to Fisher information. Now we can apply by law of large numbers, LLM. What we would have is negative 1 over n, L double prime theta 0. The second derivative of log likelihood will convert in law, convert in probability to Fisher information. Expectation. Sorry, I should write 0 here. Yep. 0, 0, 0. Yeah, this should also be 0. My bad. I forgot the 0 here because I'm having the log likelihood at 0. Okay, so this is the second result. It's about the limit of the second derivative log likelihood. And finally, we had, using those results, in our lecture 12, we derived the asymptotics of MLE. So for that, we do Taylor expansion. And here I'm just going to ignore the small terms just to make it quick, right? Just do approximation. But if you want to do exact, you can still show that it's the same. So what I'm going to do is that I will do the expansion, okay, of the first derivative of log likelihood around the true value. The reason I do this is because this is equal to 0. I know, by definition of MLE. So I say I'm just going to do approximation, first order approximation. And I'll have the difference times. Okay, I just ignore the remainders. But just with this, you can see that if we just get the term we need for asymptotics, root n times theta hat n minus theta 0, by this approximation, it will be equal. I can write it just as 1 over root n L prime theta 0 divided by negative 1 over n L double prime theta 0. Okay, now you see by 1, I have the asymptotic distribution for the numerator. For 2, I have the limit of the denominator. Then finally by Slutsky, okay, this is from Slutsky, I would have this converge to normal distribution, 0 mean, variance is 1 over Fisher information. This is what we had before from the lecture 12. Okay, so today, based on these results, we are going to talk about asymptotic distributions used in hypothesis testing. Okay, so we are to this new topic. Let's try to keep those 3 results in mind because these are the foundation. So we just look at this simple test for one parameter. Under the null hypothesis, theta equals to theta 0 versus the alternative hypothesis, theta doesn't equal to theta 0. We're going to do this. And we're going to introduce 3 popular or classical tests for tested statistics. Okay, the first one is called the Wald statistic. And the Wald statistic will be based on the MLE result. Okay, so this is the based on 3, okay, about this theta hat m minus theta 0. So this is most intuitive. The idea is that to tell whether theta, the true parameter is theta 0 or not, we use the MLE to look at how far away this MLE is from theta 0. If it's really far away, we reject the null. Otherwise, we don't reject the null. That's the intuition. But how far away is considered far away? We should consider the distribution of the MLE, right? So that's why result 3 is directly applicable. And realizing that, the asymptotics involves, sorry, I think I missed a 0 here. Realizing that the asymptotics involves this parameter, right? And we want to have some standard null distribution that doesn't depend on the parameter. So therefore, we just multiply it to the left-hand side to make the limiting distribution standard normal. That's the idea. So the Wald statistic is accordingly defined as root n times I theta 0. Here in our setting, theta 0 is the null hypothesis value. It may not be the true value, but we're testing it under the null. Okay, so we're deriving the distribution of the MLE under the null. So times theta hat n minus theta 0. This is the Wald statistic. And from result 3, we already know that it will converge in law under the null. It will converge in law to standard normal. So with this, we can easily compute the p-value, right, based on the two tail probabilities under the standard normal. Given a data set, we just compute this Wn and then see where it sits at, what are tail probabilities under standard normal. So, and also this can allow us to construct a confidence interval for theta 0 because it's nice for. This is the Wald test. Okay, the second one is called Wald's score statistic, and it is based on result 1. Based on this asymptotic distribution for the first derivative of the log likelihood. Okay, based on result 3 about this L prime theta 0. So one thing I want to remind everybody is that log likelihood is itself a random variable because it depends on x1 to xn. So is L prime theta. So is L double prime theta. They're all random, no matter which theta is. If you use theta 0 from the null, it is still random. If you use theta n hat, the MLE, then you add another layer of randomness from the MLE. Okay, so with this, the Wald's score statistic, sometimes people just call the score statistic. And SN, okay, S stands for score, or maybe I should try to be more standard, RN, okay. R and R stands for Wald. And this is based on this result. And we also want to make the limiting distribution standard normal. So we want to divide it to here. It is 1 over root n divided by root Fisher information. Okay, this is it. And again, under the null, it converges to standard normal. Okay, this is the second thing. Okay, finally, the third test, it will based on result about, I should say, it will actually be based, not on one result here, but it will be based on the difference between the log likelihood at MLE and the log likelihood at the null parameter value based on this. So clearly, we know that this one will be bigger, right? Because we try to find the MLE by maximizing the log likelihood. So this will be bigger for sure. But how bigger is considered big? That's the question we want to answer. If the true parameter is indeed theta 0, then this difference is non-zero just due to randomness in our sampling. And we want to capture that randomness and see and say whether this difference is within what we expect under random sampling or not. Okay, so for this, we need some derivation. How do we derive the distribution of this, right? It's not so obvious. So for that, again, we are going to rely on what we did over there, the Taylor expansion, and we're going to do Taylor expansion again to explain this difference. Okay, so Taylor. So let me just give this a notation. Call this difference as, actually, this is our test statistic. Call this delta n, the bigger delta, and this is called the likelihood ratio statistic. Okay, because this is just the log likelihood ratio. On the log scale, the difference is just like the log of the ratio. Right, this is equal to just log of the likelihood divided by the likelihood, right? It's this. So that's why we call this log likelihood ratio, this log likelihood ratio. But people just call this likelihood ratio statistic for simplicity. Okay, so let's do Taylor expansion on this delta n. So we would have the first order. This is the first order. And the second order, I'll just write it here. Okay, times. Okay, and for the third one, I'll just write it as okay, this theta star is just between theta hat n and theta 0. So it's just like the third order version of the mean value theorem. So this is what we did the Taylor expansion. But one thing we want to make use of is this result. Okay, from 3. From 3, you see, because we want to use the fact that the MLE at the L prime at MLE is equal to 0. So this will give me one result. I would have L prime theta 0 equal to negative theta 0, theta n hat minus theta 0 times L double prime theta 0. And for the remainder I left there, I can put it back. Okay, so I can say that I can just put it back and have it as plus 2 times theta n hat minus theta 0 times L triple prime theta star star, because this theta star star is also between theta hat 0 and theta 0, theta hat n and theta 0, but it's not the same as the theta star. Okay, this is from the 3 over there, using the fact that the MLE is a solution to the L prime. Okay, so with this, then what I'm going to do is that you see I have L prime theta 0 here. I'm going to do replacement to replace L prime theta 0 by this expression. Okay, and then you see I'll see something very interesting. So I will only be left with L double prime theta 0 and so on. So basically doing this plugging, I have, so this delta n can be written as theta hat n minus theta 0 squared, okay, times, I will have a negative L double prime here. I will have a 1/2 L double prime here. So by cancellation, I will have negative 1/2 L double prime at theta 0. That's it. And the other terms are basically from this theta hat n minus theta 0. I will have term with this and the third derivative. So basically, I'm just going to make it simple here with an assumption that is, okay, the assumption I need here, maybe I just erase it. The assumption I need here is that L, this is big OP, or maybe I just write it, divided by n. 1 over this is big OP1. So what does that mean? Again, just recall that this log likelihood is a sum of NIID. So essentially, this is just, okay, this is that. So if I can assume that the third derivative of f theta is bounded from above by a constant, then this is okay, right? Because if it's bounded, then this is order n divided by n. So together, this can be big OP1. And I said big OP because, again, this is random. So with this, I can actually write it as not yet. Okay, so with this, then if I divide, or if I multiply this by n and divide by n and divide by n here, I can have this multiply big OP1. Okay, so why do I multiply this by n outside and divide by n inside? It's that not just to get rid of this, but also from my result too, I know what this converges to, right? Negative, I just revise it. This negative 1 over n times the L double prime theta 0 converges in probability to Fisher information at theta 0. And for here, I also know it from result 3. So 3 tells me root n under null for sure, it's convergent to inverse of Fisher information. And 2 tells me this converges in probability, of course, under null as well, to, okay. So then you can see I square this and I multiply by this. What do I have? It's just like I'm normalizing this, okay? By normalizing this, I can make this just as a, without a square, I'm having, so maybe I just make it a little more clear to you. So basically what I'm saying is that these two together, what I can have is n, okay, square this, and times this. Okay, these together should converge in law by under the null to chi-square 1. The reason is that the square of a standard normal is chi-square 1. And I'm basically doing the square, right? And this term is kind of normalizing the variance of this. That's what we have. So you see, comparing this to the delta n, this term can go away because it's OP1, it go down to 0. We just differ by a factor of 2. So therefore, what we have is the distribution, asymptotic distribution of likelihood ratio test is that 2 times delta n converges under the null to chi-square 1. Okay, so this is the foundation of the likelihood ratio test, why we have the chi-square distribution under the null. Do we have questions about this part? So essentially, it's still based on the likelihood theory using the results we had before. Okay, so clearly you see the three things are very well related. The Wald statistic has an asymptotic distribution, standard normal. Wald score statistic also convergent to standard normal. Here we have chi-square 1. And we know that chi-square 1 is the square of standard normal. So in other words, these three things are asymptotically equivalent. Okay, so then why do we have all three still in use, right? What are their relative advantages? So let me just quickly summarize their differences in practice. So the first important difference for the Wald statistic, you see, is that it, as I said, is the most intuitive one. And this difference has a sign that indicates the direction, whether the MLE is to the left or right of the null value. So because of this nice form, it can be easily extended to do one-sided test. So the Wald, it can be used to do one-sided test. Okay, so like you can directly have the alternative as bigger than. Okay, that's the thing you can easily do. So you can just get a one-sided p-value. But unfortunately, it's not obvious how you could do it with the Wald score statistic or the likelihood ratio statistic, right? Under the likelihood ratio statistic, basically, we are deriving the MLE. We are under this general alternative, any theta, but for the one-sided, you need to put a constraint. And so then it becomes a constraint MLE, and things are more difficult. So this is the advantage of Wald statistic. How about the second? How about the score statistic? One thing you can notice that among the three, the score statistic is the only one that where you don't need to calculate MLE. You are just calculating the Fisher information and the log likelihood derivative and then use the null value. That's it. So you save the difficulty of calculating MLE. No MLE is needed. Okay, and also the Wald statistic is more interpretable. I already said that because of specific form. Okay, so I said Wald, more interpretable because of the test statistic form. But finally, there's one thing that is advantages of using the log likelihood instead of just the Wald statistic, right? You see, even though its asymptotics depends on the log likelihood theory, but in fact, the form doesn't involve log likelihood at all. So for the score and I just read LRT for likelihood ratio test, they have a very big advantage is that they are invariant under what we call reparameterization. So what does that mean? It means that sometimes we can specify the model using a different set of parameters. I think a very typical example is the gamma distribution. Okay, so if you check Wikipedia about gamma distribution, you can see there are two ways to parameterize the same distribution, using the rate parameter or the other is something else. Yeah, so basically, then these two are just the inverse of each other. Another example is the negative binomial distribution. You can also parameterize in two different ways. So therefore, even though it's still the same distribution, but let me just say it. So let's say I have eta equals to g theta. Okay, and so eta 0 is equal to g theta 0. So basically, we want that testing the null hypothesis of theta equals to theta 0 or testing eta equals to eta 0. We want to have the same result because the parameterization is not the key. But if you use the Wald statistic, then you may get different result. So it's not invariant. But if you use the likelihood, log likelihood, then the change of variable thing, although you will have the, once you change the parameter for the likelihood function, you are going to do the change of variable formula for the density function. But still, it will be absorbed into the Fisher information as well. So you will have some cancellation here and some cancellation there. So therefore, you will still have the same test statistic. after reparameterization, but that's not the case for Wald test. Okay, so what we have talked so far is the univariate test, right? Theta is one-dimensional. How about multi-dimensional? What if theta is a vector? So for that, let me just try to quickly write a multivariate version without derivation. So you will see the connection by just, the algebra. So for what if the theta is k-dimensional? Let's put it more general. So for example, we have seen this in linear regression by testing whether the whole coefficient vector is 0 or not, right? So in that case, we still have Wald test, score test, and the likelihood ratio test. Okay, so for the Wald test, again, every test statistic is supposed to be scalar so that we can talk about its distribution p-value very easily, right? So we want a scalar value test statistic. Then how do we do it? So intuitively, if we do this, we are going to have k differences. How do we aggregate them into one? The very natural thing to change a vector into a scalar is to do its own inner product, right? To get its norm. So therefore, here we just have this defined as, so root n after square becomes n, and we have the vector theta n hat minus theta 0. So now this is the k-dimensional vector. And it needs to multiply a k by k Fisher information matrix. We put it in the middle. Okay. And we multiply by its transform. That's it. So you see, this is k by 1. Oh, sorry, this is 1 by k. Oh, sorry, this is the row vector. My bad. This is correct. I need 1 by k here, k by k, and k by 1. So finally, I get a scalar valued Wald statistic. This is the Wald statistic. For the Wald score statistic, we do something similar. So now you recall for the first derivative of, right, this is like a vector value. And then for that likelihood, in our previous lecture, we introduced the notation L dot. So that is, if you recall, we introduced L dot, this to be a k 1 by k row vector in our previous lecture. So we're going to stick with that notation. So again, n will be squared as 1 over n, and root will be squared. And then we have L dot at theta 0, a row vector, times, now we need the Fisher information inverse. And finally, the gradient derivative. And in some contexts, you may see people write this using this as the gradient, and it's basically the same thing. Okay, this is the Wald score statistic for the multivariate version. Finally, this likelihood ratio statistic. Now it's easy, right? Still the likelihood difference. We don't need to change anything because this becomes a vector, this becomes a vector. We need to do something, but this stays as a scalar. So it's still it. And then what are the distributions for those multivariate version? So as I said, for this, you can see it's basically for each standard normal, we take a square and we have k of those, right? And then we add them up. So naturally, you will have Wm converges under the null in law to chi-square with k degrees of freedom. It's like the sum of k squared normal, standard normal, right? This inner product is basically the sum of the dimensions. Same as Rn. So Rn also test this. Finally, likelihood ratio. Okay, so for this, it's not very obvious just by the form, but if you look at all our derivations here, so you would actually see that we also need to change this to be like a vector inner product, right? Because the difference is just a k-dimensional vector. And also this second derivative becomes a k by k matrix. So we also need to change to the vector form. So again, this converges to chi-square k. So basically, you see, they now in this multivariate version, they all converges in distribution in law to the same chi-square distribution. And the degrees of freedom is the number of parameter difference between the null, right? In the null, you set all the k parameters to fixed values, but under the alternative, you allow them to change freely. So this is the difference in the number of parameters. Okay, so any questions regarding the 3 tests? Actually, in the linear model class, which I used to teach in the course number is 205. So in that class, we actually talk about Wald statistic and the likelihood ratio statistic. And so here is the score statistic, which is also used. So then you can see that we have multiple tests for the same hypothesis. Then how can we know whether a test is valid or not? Okay, so to answer that question, let me just try to write down some criteria for a valid test, or we say a consistent test. What do we mean? Okay, so first of all, let's say that if the test is to reject the null, if the test statistic Tn is greater or equal than some constant Cn. And here it depends on the sample size, we know that. Okay, so in this case, if we want the test to have asymptotic significance level alpha, if this test is satisfying this is at the significance level, what we need is that the probability under the null hypothesis, I say theta 0, that this test statistic is greater or equal than the constant, this probability must converge to alpha as n goes to infinity. This is what we need this test to satisfy. Okay, how about the power? The power is also the probability of rejection, but now not under the null, under some other theta. Power, we write p theta when theta is not equal to theta 0, so the null doesn't hold. We will need this rejection probability as n goes to infinity to converge to 1, which means that with infinite sample size, you should always reject a null. This makes sense, right? Because with infinite sample size, you see the whole population, then you definitely know whether theta is theta 0 or not. So we need those two things to make the test a valid test. Okay, so speaking of this, so recently I wrote a perspective article about distinguishing hypothesis testing from binary classification, because actually in practice, it's usually sometimes confusing about whether a real problem should be better formulated as a hypothesis testing problem or a binary classification problem, or more exactly, a multiple testing problem where you have multiple tests or a binary classification problem. So if that's something you're interested in, I can post that paper to RCCLE under week 10, so you can read it when you have time. But that's just a note following this. Okay, so the reason I mention this is because this is very important for our testing. But for binary classification, even if you have infinite training sample size, you may still not do perfect classification, right? If the two classes are just overlapping, they share some ambiguous boundary. In that case, you can never do perfect classification. And that's a very important difference between the two methodologies. So that's why I want to clarify that in that perspective article, and I'll send it to you. Okay, so these are the three tests. And to wrap up, right, I also want to mention a very interesting topic about the asymptotics of the Pearson's chi-square test. So unlike what we said about the three tests, this is a more specific test. It's about multinomial distribution. So basically here we have this case as we have x1 to xm. They are k-dimensional vectors, okay? And they are IID from a multinomial distribution with only one draw and a probability vector of k categories. So for this, I just write P from this k-dimensional simplex. This means that, so if I write P as P1 to Pk, what it means is that all the P1 to Pk are non-negative, and also their sum is equal to 1. This is what we mean by a simplex. Okay, so from this, then basically you can see what will be my x1 to xn. My each xi, if I expand it as xyi1 to xik, they are zeros, and k minus one of them are zeros, and only one is 1. K minus 1 zeros, only 1, 1, okay? So that's how each xi would be. So it basically means which category did I draw? One of the k categories, and I can only draw from one category. And I did this independent draw for n times. That's why I have x1 to xm. Okay, then what does Pearson's chi-square test do? Sometimes people call this goodness of fit. It just means that I want to know whether some pre-assumed probabilities P1 to Pk agree with the results I draw. Okay, so what do I draw? So we often summarize those x1 to xm as the number of draws from each category J. So we define Nj, the data, as the sum of xij. Take the sum over the xi's, right? So out of the n draws, how many times I get 1 in J category? Okay, and then what's the Pearson's chi-square statistic? So assume that our null hypothesis is the probabilities are P1 to Pk. Some presumed probabilities is usually like 1 over k, just by assuming the k categories have equal probabilities. I want to test for that. So if this is our null hypothesis, then the chi-square, I'll just write it here, Pearson's chi-square statistic is actually, I'm just going to write this form, but don't confuse this with the chi-square distribution, even though it does follow chi-square distribution, but we will just treat this as a statistic notation. It's defined as this: summation for the category J from 1 to k. In the numerator, it is the square difference between the observed count in the jth category minus expected count. Expected count is the total n times pj. Okay, and denominator is expected count. So that's why many people remember this formula just as, I remember people say OJ minus EJ squared divided by EJ. O stands for observed, E stands for expectation. Okay, so what is the asymptotic distribution for this, right? This is something we want to develop here. So for NJ, now with our central limit theorem, we have seen it for so many times. You can see that it's basically a sum, right? Sum of x1j to xnj. So what we know is that if we take the average of these things, so by central limit theorem, you know what we would have is root n xn bar. This is k-dimensional minus the expectation p vector. It will converge in law to a k-dimensional normal distribution. I'm just saying 0 k-dimensional vector and the covariance matrix. Okay, so in the covariance matrix, if I write here, let's say for the JLth entry, it will be what? In this covariance matrix. So it depends on whether J equals L or not. If J equals L in the diagonal, it's basically the variance of Xij. If J doesn't equal L, it's the covariance of Xij, Xil. Okay, it's the covariance of the dimensions. And so what do we have? Because for Xij on its own, we know actually it follows just Bernoulli with probability Pj being 1, since it's 0, 1. Xij is a binary value. So therefore, we know this is just by the Bernoulli variance, it's Pj times 1 minus Pj. Okay, how about the covariance of Xij, Xik? For this, I'm going to just use the definition of covariance. This is equal to expectation Xij, Xik minus the expectation, the product of each expectation. And we know that's Pj, oh, not K, IL. Sorry, I made a mistake. IL, yeah. Xij, Xil, Pj, PL. For this expectation, by my definition of this draw, I can never have both equal to 1. One of them must be equal to 0. So therefore, this is 0. So that's why I have the covariance as negative PJPL. So put it together, I have the form of my sigma matrix. Okay, I have my sigma matrix, which takes this form. It's a K by K matrix. I have P1, 1 minus P1. The whole diagonal is like this, PK, 1 minus PK. But for the off diagonals, I would have negative P1, P2, up to negative P1, PK. Okay, so all the off diagonals are like this. So what's the issue with this sigma matrix? So if we think that with this, we're done, right? So can we simply do something like the test statistic, right? Can we do something like what we did before? N times xn bar minus P transpose times sigma inverse times xn bar minus P. Wouldn't this just converge to say something like chi squared K This will be my natural guess, right? Given what we have done before. But why this doesn't work? The reason is this, because the P is a simplex, okay? This is so special. If you take the sum of each row, you will see that it's equal to 0. So every row has a 0 sum, which means that this matrix is singular. It doesn't have an inverse. So the issue is that this doesn't exist. So that's why this approach will not work. And we need a fix. So how do we fix it? So this is a very useful approach that we should all bear in mind. So given that we know every xi sum up to 1, right? Only one of them is 1. And also the pj sum up to 1. So then therefore, we should only keep the first k minus 1 dimensions. We don't need the last dimension because the last dimension is implied. So with this, we define just yi. Okay, for yi, we just take the first k minus 1 dimensions of xi. Okay, that's my yi, my new observation. And I also pick p star just as p1 to pk minus 1. And correspondingly, I pick the first k minus 1, this the upper diagonal called that a sigma star. Okay, so with all these, I can show that for this sigma star, it is invertible. So I get rid of the last row, last column. Now it's invertible, and it has a very interesting form. So this sigma star inverse, if we do the calculation, we can see it has a very nice form. It is 1 over P1 plus 1 over PK, okay? Last one, 1 over P1, 1 over PK minus 1 plus 1 over PK. Because this is K minus 1 by K minus 1 dimensional. And except the diagonal, everything else is 1 over PK. So therefore, I can write this as just a diagonal matrix P1 over P1 to 1 over PK minus 1 plus a constant matrix with all the same entries plus just I write 1 over PK times a matrix of ones. Okay, and this is K minus 1 by K minus 1. Okay, so with this nice inverse, now you see I'm going to change my test statistic, not this one, but just use my new yi's. So now the test statistic becomes just, okay, n, still n, yn bar minus p star transpose sigma star inverse yn bar minus p star. Okay, because now I only keep k minus 1 parameters, so then this asymptotic should converge under the null to chi-squared k minus 1 degrees of freedom. And then finally, interestingly, everybody can do the verification on your own. Given this nice form of the sigma star inverse, this form, if you do the simplification, you can show that it's actually what we have in the Pearson's chi-square statistics. J from 1 to k, nj minus mpj squared divided by npj. You can verify this. And actually using this form, that this is equal to this diagonal matrix plus this constant matrix, you can see that it's very interesting. And also the reason we can introduce k back is simply because we have nk equals to m minus n1 minus nk minus 1, right? And pj equals to 1 minus pk 1 minus p1 minus pk minus 1. So using this relationship, we can actually show that this thing just happens to be the Pearson's chi-square statistic. So therefore, the asymptotic distribution of this Pearson's chi-square statistic is chi-square with k minus 1 degrees of freedom. And now we can actually derive this by ourselves using the central limit theorem as the starting point. And also I would say intuitively, the degree of freedom, the k minus 1 also makes sense because we have that add up to 1 constraint, right? Given that you can only change k minus 1 things. Okay, so I think that's all I want to say, and that concludes our lecture. And so I hope that we can use the rest of our time for the online evaluation if you do have your phone or computer, because I remember in the last few years, usually if I feel like sometimes the response rate is usually very low. So that's why I think talking to my colleagues, and I learned that good idea is to leave some time in the lecture and so that the students will remember to do so. So I really appreciate your feedback. And also the deadline is just this Saturday, right? So they won't wait for long. And also I'll stay here. So in case you have any questions about the presentations, you can ask anytime.
The presentations, just to recap so that I got it right.
Let me try to stop the recording first.
Okay.